Here is problem 7 of the test. Once again, if you need more time to read the problem or open it up in another tab, feel free to pause the video. So now we begin. What is the problem about? Well, this problem is about the binomial expansion for non-integer exponents. It gives us the explicit formula, and we want to find the first 3 digits to the right of the decimal point of some number, some binomial expansion. So now what's special for this problem? As in, what separates it from other problems? Well, we see that there are some very weird numbers in our representation. We have 10, 2002, 1, and 10 over 7. 2002 being the year of the test, it should be just an arbitrary value. But the other ones are placed here for a purpose. So 10, 1, and 10 over 7 have a purpose. And we can immediately see what 1 does. 1 is y in this binomial expansion. And in here, in the binomial expansion, we're multiplying by powers of y, which is powers of 1, which is just the same. 1 to the power of anything is just 1. And something else that's odd is the answer format. We want to find the first 3 digits to the right of the decimal point. This means that any integer value does not matter. We can just cancel it out. And any term in this binomial expansion that is very small, that is believably small, will not affect our sum enough to nudge it up 1 thousandths. So any integer doesn't matter, and any term sufficiently small doesn't matter. So now, what relations are there? Well, here it seems like it just gave us the binomial expansion, and that there aren't many relations that we can use to solve the problem. So we can just leave it as is and then proceed to the next part. If we find something useful, we can always go back and fill it in. So how can we simplify the problem? So we can try plugging in the first few terms and see if we get anything. So we have x to the r. This is 10 to the power of 2002 to the power of 10 over 7. And this is equal to 2002 over 7 being 286. So 2,860 is the first term. The second term is r x to the r minus 1. Once again, y doesn't matter because y is 1. And this is 10 over 7 times 10 to the power of, well, r minus 1 will be 3 over 7, so that will be 286 times 3, which I'm not going to bother evaluating. And third value is 1/2 times 10 over 7 times 3 over 7 times, well, this time r minus 2 will be 10 over 7 minus 2, which is negative 4 over 7. So we have actually a negative exponent. Negative, or 286 times negative 4. And now hold up. 10 to the power of 286 times negative 4 is a very small number. And this is just the exponent in the third term. And as we keep decreasing r minus 3, r minus 4, r minus 5, we will get a more negative answer. So, and we will get a more negative exponent. So the negative exponent grows more negative. But how can we be sure that just the combination of some of these terms, or maybe just one term in particular, is large enough to influence the first 3 digits? So we must look at the coefficient, this coefficient. And for some general, k is greater than 2, which forces r minus k to be 0 or negative. And this gives us pretty much a negative exponent. The coefficient is r times r minus 1 times all the way to r minus k minus 1 all over k factorial. So now, how can we make sure that this doesn't generate a very large ratio to offset the very small value we get from the negative exponent? Well, r is 10 over 7, and 10 over 7 is pretty close to 1. So we can use that as an approximation. But we have to be careful here. We have r and r minus 1 as terms in the product. And r minus 1 will be 0 if we sub that in. And that will give multiplication by 0, which we don't really want. So instead, we keep the positive values as is and only substitute for the negative values. And why is this good? Why is substitution r equals 1 good? And this is because 1 minus the last term, k minus 1, will be less than 10 over 7 minus k minus 1, which is a more negative value, which generates a larger ratio. So now if we substitute, we keep the numerator, so this is the numerator, 10 over 7 times 3 over 7, and all other terms will be negative, so it will be something along the lines of negative 1 times negative 2 times all the way to 2 minus k. And this, if we take the negative of all these inner terms, this will be equal to 30 over 49 times plus or minus k minus 2 factorial. And now if we divide it, we get that the coefficient is 30 over 49 times 1 over k times k minus 1. And this grows smaller as k increases. So ratio will never be enough. And this means we can practically ignore all terms beginning with the third one. So now we want to find the first 3 digits after the decimal point in our previous value, which is 10 to the power of 2860 plus 10 over 7 times 10 to the power of 286 times 3, which is 858. And once again, 10 to the power of 2860 is an integer, so it does not affect our final answer. Therefore, this just goes to 10 to the power of 859 divided by 7. So what is this? Well, we know that 1 over 7 is equal to, in decimal form, 0.142857, repeating. You should have this memorized. And this repeats every 6. And since we have 10 to the power of some number, so we're multiplying 1 over 7 by a power of 10. This will shift the decimal point 859 places to the right. Which means, since 859, if we take it mod 6, this is equivalent to 1 mod 6. And this means that our ones digit will be 1. Because 859 is some number of these repetitions and then adding on the beginning 1 at the end. And thus, the first 3 digits after the decimal point will be 428, which is the numbers that come right after 1.